let's get started. First of all, I want to thank everyone for making to this morning talk. I hope everyone got some coffee beforehand, because we're going to cover quite a few of topics regarding microservices. So just before the talk starts, I want to start with a quiz to make sure the audience is awake. Please raise your hand if you heard about microservices. OK. And keep the hand raised if you're actually using them at work. And keep the hand raised if, like, at the company, only a handful of people working on a microservice, if they're like really a microservice. OK, almost no one. And also, raise your hand, please, if you just heard the buzzword microservices and just want to know more about them. Wonderful. So we have a pretty diverse crowd here. And this talk will consist of two parts. First, we'll cover microservices. It will be a brief introduction into them to make sure we understand advantages and disadvantages of them, just to make sure we're on the same page. And in the second practical part, we're going to talk about how to mitigate the disadvantages of microservices using Kotlin and all the perks of JVM ecosystem. So let's jump into the talk and do a brief introduction to microservices. So probably everyone in the audience at some point wrote an application that looked like this, whether you were learning how to do the engineering or something like that. It's a classical three-tier application where you have presentation, business logic, and data access layers. They live separately. In the most cases, probably you have two monolithic applications. You have a separate presentation layer. In a modern stack, it's probably just a Node.js. And then you have this business logic and data access living in a separate application. And today, we're going to focus more on this layer, on this gray area. And to be fair, in a modern world, you probably don't have just like one application. Architects are trying to split this business logic into multiple modules. And this architecture is very old and can scale tremendously. And many multi-billion companies built that way. For example, Twitter.com was at some point just a huge-ass Ruby on Rails application before they switched to microservices, and now they have thousands of them. So let's talk about disadvantages of a monolithic application that look like this. Like, first of all, the release cycle is the same for everyone. If you have like 100 engineers, they release all the features at the same time. It becomes a challenge just to maintain the release cadence of like weekly releases. Like usually it's probably months, and sometimes you just cannot release because of all the bugs you introduced. Another disadvantage is it's impossible to enforce boundaries between these modules. It's really, you can try to, but unfortunately, people tend to go the easy way and avoid these rules and boundaries. They will tell you that it's a necessary hack to get in time for a release, and they will fix something, but unfortunately, there will be another release after that, and it will basically never end. And the technical debt will accumulate altogether, and it will affect everyone. But there are also a lot of advantages of oh, by the way, it will also be pretty hard to debug performance issues, because all the modules will compete for CPU resources, and just one module can bring the whole application down. And but there are quite a few advantages. Like, first of all, it's very easy to start. You just start with a hello world application and continue from that. It's just start simple, don't over-architect. It's also easy to contribute to all the parts. It's one application, it lives in one repository. There is one code style for the whole application. It's pretty easy. And also, it's super easy to debug logical bugs because of the same reasons in just one single application. So now let's talk about microservices. So microservices essentially is those modules split it in separate services, separate running applications. And from the slides, you can see I just changed modules to services. And that's pretty easy. But internally, once you switch to such architecture, it actually changes everything, because now there is a lot more async workflow going on. And let's first talk about advantages of such architecture. It's an independent lifecycle. So every team works on a separate service. They can release it separately, daily, monthly, weekly. It's up to them. It's super flexible. Also, well-defined boundaries that are impossible to cross, because you have services running separately. Each service defines an API, and other services can only use the API that is provided. You cannot go and access the database directly, and so on and so forth. So each service will define an API. Also, different services can even be written in different languages, using different frameworks. It's so much flexibility, but unfortunately, flexibility is not always great. With great flexibility, there is great responsibility to not mess things up. And you probably want to have some rules around what frameworks and languages you want to use. But let's talk about disadvantages, which are mostly interesting for us today. So probably one can say that disadvantages of microservices is actually opposites of advantages of monolith. So it's really hard in the beginning because you need to start with microservices. It's hard to contribute to different microservices. They can live in different repositories. They can be written in different languages. They can use different life cycles, different code styles, and other things. It's also hard to debug in a distributed system, because you don't know what's going on there in most cases. And before we jump into the practical part, I just want to tell my thoughts about monolith versus microservices when it comes to speed of development. Of course, with a monolithic application, you will get a lot more done in the beginning. It will be a rapid growth, but then eventually it will slow down because of all the technical depth accumulated in the application. With microservices, on the other hand, you will have a slower start because you will need to do some boilerplate and preparation, but eventually it will pay off. So let's do the practical part, which is probably the most interesting for you. So first I need to make a disclaimer. It's just one way of doing microservices. There are so many frameworks for doing them and just so many options. This is based on my experience working on building Cirrus CI. It's CI as a service. It's written in Kotlin. There are 22 microservices at the moment. And everything that will be described in the presentation works perfectly in production. So why Kotlin? I don't think I need to tell you how Kotlin is great. We are at KotlinConf, but we're going to talk about how to use Kotlin for writing business logic, and then we will try to build the application from bottom to top to how services will interact with each other, and then finally how to manage these microservices using Kotlin. So once again, I don't think I need to convince you to use Kotlin for writing business logic, but just a little bit of my thoughts about Kotlin. I have extensive experience with Java and Scala, and like Java is great, but it's not evolving that rapidly. IntelliJ, of course, makes it much easier to write, to generate. It like generates all the things and tries to hide others. Scala is also great, but it's like just too many options. I saw Scala written by Java engineers like Java, Scala written like Ruby by Ruby engineers, and it's hard to get the canonical Scala. And with Kotlin, I feel that it just, like Kotlin as a language guides you to towards an elegant solution. With like Scala, for example, sometimes I spend more time rewriting the solution just in a nicer way. With Kotlin, it just happens. So let's talk. So since now we convinced ourselves to write the business logic with Kotlin, let's talk a little bit about how these microservices can interact with each other. Let's talk about remote procedure calls. So any API call that you do in the application, it's a remote procedure call. You probably remotely execute some procedure. In most of the cases, it's just REST. It's probably the most popular one. Usually, it's JSON over HTTP. It compresses well, but unfortunately, it's CPU expensive to parse. And in most of the cases, there are big generic responses. So on the right-hand side of the slide, you can see a REST API from GitHub, which returns information about a user. And you can see if I want just to know the login information of a user, I will get the login, but also 39 fields that I just don't care about. And responses are usually not typed if you don't use some framework that generates everything for you. And if you want to use some third-party API, you, in most cases, will need to figure out the types on your own. So evolution of REST is probably GraphQL it's another way of doing RPC. So it's still JSON over HTTP. It still compresses well. It's still CPU expensive to parse, but now it's typed. There is GraphQL schema on the right-hand side. You can see in the top the schema definition. It's also there is null safety. You can also do pretty flexible queries to make sure you get only information that you need. So you can see that here we just request login information for a user. It's still GitHub API, but now it's GraphQL. And in the response, you will get only information that you need. And I feel that it's perfect for external clients. For example, like GraphQL was created at Facebook, where they have so many billions of installations of applications, and they need to manage basically thousands of different versions of applications installed on the phones and not updated. And that's a perfect way for not caring about backward compatibility, because like old clients will use old queries, new clients will use new queries, and everything will work. But let's talk about something more interesting, gRPC. gRPC is actually a binary protocol. So on the right-hand side, you can see that it's not really human readable. Unfortunately, it's not JSON. You cannot just look at the response or request and understand what's going on there. It's protobufs over HTTP. So it's a special binary format. You can see the definition of a user, which is called message. It's super easy for machines to parse. There is you don't need any like state or something. The objects are predefined. The parsers know what to expect. It's typed and it has really high performance clients. But the interesting part here is not the format itself or gRPC. The ecosystem around gRPC is interesting. So once you have the definition of a service, you actually don't need to care about parsing something. gRPC compiler plugin will just generate for you clients and servers. So here on the slide, in the right bottom corner, you can see that gRPC generates builders where you can build requests and messages, and it will automatically serialize and deserialize them. So let's get to an example. I think everyone at some point wrote a calculator where you just have a math expression and you want to evaluate it. So in this practical part, we'll try to build a distributed calculator. It's available on GitHub if anyone wants to look at it. So in our distributed calculator, we will evaluate mathematical expressions, and each operator will be a separate microservice. So we will have a microservice to multiply things and perform additions. So, and you can see that it perfectly translates to API calls. So when you parse the expression, you need to first call addition microservices twice, and then with the result of it, finally call multiply service. So here's a gRPC definition of our multiply service. You can see that it defines just one RPC call, basically just calculate things. And there is a request and response that will be automatically generated by gRPC compiler. So here you can see that gRPC compiler will generate for you a base class for your server. You just simply need to extend it and override the calculate function. And you will get the request, which will be deserialized for you by the framework. And then you will have an observer where you will need to submit the response for this RPC call. And that's simple as that. After that, you can start the service. You don't need to do any other configuration. It's like a few lines of code. So yeah, here you can see that we submitted. And in case of an error, we also made sure that observer knows that the error happened. So for clients, the situation is a little bit more interesting. For clients, clients are also generated. And in order to use the client, you first need to create a channel. But channel can be, in this case, an HTTP2 channel. We can, out of the box, enable retries for various errors that are retriable. We can configure how many retries do we want to perform before giving up. And there are so many other things that you can do with gRPC framework. There are so many other useful features for like distributed tracing, and just like monitoring and so on. And once you have the channel, you can create a client, and then you can use the client as any other object in your application. You just use method calls, and you will get listenable features, Guava listenable features. But of course, we're at KotlinConf, and like I personally prefer more coroutines, and I prefer to wrap such generated clients into nice Kotlin interfaces and classes with data classes and so on. So we can define something like this, which don't know anything about like listenable features or what's going on there. And the implementation will be super simple. You just use the server, the client that generated by gRPC, and use Kotlin coroutines Guava integration to convert listenable features to coroutines. But the interesting part here, which is actually unique for gRPC, gRPC supports not only Java, it supports Go, Ruby, I think Python as well, and C++. So it's multi-platform protocols, and there are many other integrations, probably not that popular, but still available. So the unique thing about Java implementation of gRPC is that you can have in-process channels. So we saw that you can have a channel that communicates to a remote server located at some host name, but also you can do in-process when you want to run multiple services in the same JVM, so they can talk between each other, and it's super useful for testing. And we'll see it a little bit later in the talk in the demo part. So now, since we figured out that we are writing the application and the business logic in Kotlin, and also that we are using gRPC for communication between services, we need to talk about code organization, because as I mentioned, all the services can live in separate repositories. They can be written in different languages. So you need some rules around that. So let's use a monorepository. So all the services will live in a single repository. It's probably a good topic for another talk to discuss multi-repo versus monorepo, but you'll see in a minute why it's very useful for such microservices. So for code organization, since all the microservices live in one repository, we will create 5 different modules for each microservice. There will be one API module that defines gRPC definitions. Then there will be implementation module that just implements the server and extends the generated server definition and overrides necessary RPC calls. Then there will be a client with our fancy Kotlin wrappers around generated clients. Then there will be a config module, which will contains different configurations like TTLs and how to deploy your microservice to Kubernetes, for example. We'll see how to do it in the very last part of the talk. And then there will be a special testing module that will use these in-process channels to create not mocks of your service, but real services that you can use for testing. It's pretty complicated, I know. Let's see if you have another module, another microservice B, for example, that uses service A. It will have absolutely the same structure, but when you will want to use service A from service B, you will add only 2 dependencies. So service B implementation will depend on configuration of service A, and testing module for service B will depend on service A. And in this case, you can see there is no dependency between implementations. So service won't depend on each other. They won't be able to use utility methods or something like this from other services. You will need to extract them in separate libraries. So since now we have 5 modules with for every service, and if you have like 20 of them, you will end up with like 100 sub-modules only for microservices. So how to build all of them with Gradle? So like first of all, in my case, it's like 208 sub-projects, so 22 microservices, 110 modules only for microservices, and there is another 100 for different libraries and utility things. So just parallel execution and remote caching working perfectly fine. Mostly time spent during compilation of implementation of services, which are the most heavy one, but they don't change that frequently. And other modules are very small and also don't change that frequently. So remote caching just saves things tremendously, up to 10 times. And I also prefer to use implementation configuration with a few usages of API. So usually people use compile, which will expose the same dependency to other dependencies. So you will get transitive scope of all the dependencies, and you will somehow get things you probably sometimes don't want. With implementation, you will need to explicitly define what you want to depend on. And also use a libraries plugin to have global versions of all the libraries. And of course, perform a regular auto upgrades of libraries to make sure everything is up to date. So here is an example how to use the libraries plugin. So as you can see, you use it as usual string literal, but you don't need to specify the version. The version will be taken from a central location, so all the services will use the same versions of all the libraries. So let's switch to the demo. So this demo is available on GitHub, as I mentioned before, so if anyone will want to play with it, feel free. So as you can see, there are several services defined. There is the main one, calculator. There is three operators that we have, and one example service that we can use for generating like skeletons for other microservices. So each one of the microservice has 5 modules, as I mentioned: the API that defines protobuf definitions, and client with the clients configuration that will define some useful TTLs or like Kubernetes configurations. And now let's try to run some tests. So as you can see, in our case, we're hitting this KotlinConf demo test, where we create these test providers from the testing modules. We do some boilerplate, which is like needed, unfortunately, but I prefer that instead of some magic. And you can see that now we're trying to run our demo and try to evaluate expression that was on the slide before. And now the interesting part is we will be able to jump from one service to another, because they all are running in the same JVM and using in-process channels, so you can easily debug issues in your tests. And here you can see that we hit the addition service that will add 1 and 2 to get 3. And after that, we will end up in multiply service, where we are multiplying 3 and 7 to get 21. And we will finally get back to our test, and we will just get the right answer. Great. So once again, this demo is available on GitHub. There are quite a few, not quite a few, there are a few advanced things that are missing from this demo, but because of the time constraints, I just don't have time to cover all of them. Feel free to jump into issues marked with to-dos to discuss how to add health checks, monitoring, or how to handle request cancellation gracefully. Okay. So since now we know how to build microservices, using Kotlin for the business logic, using gRPC and Kotlin wrappers with coroutines for service communication, using Gradle with Gradle Kotlin scripts for building them. Let's talk how to deploy them and manage them. So it's pretty standard now to use Kubernetes. For those of you who are not too familiar with Kubernetes, it's a container orchestration system. It has built-in service discovery and load balancing. It's self-healing. It has many features like rolling deployments, horizontal scaling, and many others. But the interesting part for us is how Kubernetes API is working. So everything goes through the API. You create objects, API objects, and Kubernetes takes care of making sure that the whole cluster looks like you defined it. But unfortunately, it's YAML. You will write a lot of YAML, and this is just horrible. And there are a lot of tools to generate YAMLs for you for services. It's not typed. There is no intelligent IDE support. It just doesn't scale that much for big organizations. So we are at KotlinConf, so we can use Kotlin to rescue us from that. So we can create a custom DSL, custom statically typed DSL for defining service. So on the slide, on the right-hand side, you can see the YAML definition that you use to define an ingress controller to expose your front end to the world. And then on the left-hand side, you can see Kotlin DSL in action. So you can see there is a completion, there is it's statically typed, so it's making sure that you don't, for example, define, you mess up tabulation and define something in the wrong thing, and there is like no validation for that, and then you spend hours to debug the issue. But the benefit of using Kubernetes, for example, can be so you can create a base deployment. So you can actually inherit these objects. So for example, you have a base deployment that defines the service name that you want to deploy. You can do some things like resources that you want to define for this service. And then each microservice can extend this base definition to do some customizations, for example, increase the termination period or increase failure count because there are like many dependencies of the service. And that's pretty much it for me. If you have any questions, you can ask me on the mic, or you can tweet at me or DM me, or feel free to jump to the GitHub issues for the demo, and we can discuss some particular parts there. Thank you.